So I'm going to spend most of this talk talking about how to verify stateful networks, and in particular, how to scale verification to stateful networks. So to start with, let me go through what stateful networks are. So we've heard a lot about SDN and other things where you can program switches. You have controllers that program switches, but these switches contain rules, and these rules change fairly slowly. They change in response to either policy updates or changes to topology. By contrast, things like Middleboxes often have forwarding behavior that depends on the state. For example, stateful firewalls will forward or drop packets depending on whether connections have been established. Now, these have both sorts of things, both sorts of content. So they have rules which, again, continue to change slowly because they change based on policy changes and topology changes, but they also have state that could change at the rate of packets. So every time a connection is established, so every time you see a TCP SYN packet, you might set some state. And similarly, you might even do it every time a packet is forwarded because you want to reconstruct the payload. So we want to consider these networks, but perhaps one question is, why consider these networks? We've had a lot of work on network verification which hasn't looked at this because it's been easier when we don't have to deal with the state business. The thing is, Middleboxes and other such stateful devices are quite common. So in 2012, a survey found that 1/3 of all network devices in enterprise networks are stateful. So ignoring them seems a bit strange. And then with the rise of things like NFV and other things, the number of these devices is only growing. And finally, we've all of this recent excitement around programmable switches with P4 and such, and these contain registers which are again stateful. And most existing verification tools have completely ignored this problem, and the little work that has been done on this has some other issues with it, so, which I'll discuss. So that's one reason. But the other thing is, even independent of this, state actually impacts the sort of questions we should be asking. It impacts the invariants we care about. So like many other work all of the other work in the past, we also focus on questions of reachability and isolation, which are basically questions of the form, can packets from some host A reach some host B, for example? But when we add state, you need to consider some other things. In particular, you might want to consider some temporal aspects. I'll go over this in detail in a slide. And there's actually this problem which was mentioned in Daniel Firestone's talk yesterday. We want to consider beyond just packets. You want to think about connections, data, and other such primitives. So let's start with the temporal invariant bit. So this is a very standard network, and if you put it through HSA or any standard technique today, the question you ask is, can user 1 receive packets from server 0, or can you check that user 1 receives no packets from server 0? And the problem is, because it's a stateful firewall, and hence it allows packets to go through once user 1 has established a connection, this question is trivially going to always return true. But as an operator, what you probably care about is, could user 1 receive these packets if it hadn't opted in, if it hadn't gone and created a connection? We're fine with receiving packets after we opt into this, to this business of receiving the packets from server 1. The other bit which I talked about is, so Daniel had some points about why we needed to deal with connections. I'm going to talk a bit about data, for example. So consider this very simple network, and where we say, well, I can verify using HSA that user 1 can never receive packets from server 0 because I've installed the appropriate firewall rules. The problem is, this invariant happens to not be very meaningful because any data that originates at server 0 can subsequently be received by user 1 through the cache. So really what we want is another property which says, what we care about is not so much whether a packet that was sent by server 0 directly reaches user 1, but was data that was stored on server 0 ever received by user 1. So we want to be able to ask these additional questions. And to do that, we really need to start accounting for state in our verification tools. So having explained why we care about stateful networks, I briefly want to give you an overview of what has been going on in the verification space so far. So we've had a lot of great work on verifying static networks, and this includes both work on verifying switches, verifying controllers, and as we just heard, work on how to generate code for controllers and other things. And this includes things like HSA, Veriflow, Netcat, things that we all have heard about a billion times in this conference. More recently, last year, we had some work on testing networks with mutable datapaths. So the idea here was you take some code and you use symbolic execution and other techniques to generate out packets that trigger different code paths. And finally, we've had work on using symbolic execution itself to verify networks with mutable datapaths. That was published in SymNet, that was published in the SIGCOMM. But again, there are limitations to the kind of networks you can verify with this. So now let me give you an overview of our approach to doing this verification, which we call VMN, or Vermin. So Vermin is a system for scalable verification of stateful networks. And our verification methodology is to use model checking. We have a 4-step process where we first model Middleboxes. Then we take these Middlebox models and we combine them to form a model of the entire network. So basically, this is where we take the topology into account. We add in some logical invariants, and then, like many other people, we translate this into first-order logic formula, or into formulas that are acceptable to Z3, and we feed it to the SMT solver, which tells us was there a problem or was there not a problem. In the interest of time, I'm mostly going to focus on the question of how to model Middleboxes in this talk. The paper has details about the rest of these steps too. Okay, so when you're modeling Middleboxes, there are a few approaches that you can take. The one that I think is well liked in the systems and networking community is to just somehow take the code and extract the model out of it, because you don't have to, you know that it is exactly what you want to model. The problem is that this code is often at the wrong level of abstraction. So in particular, because we need to achieve really high packet rates with all of these NFs that we're writing, we commonly write our code in terms of treating the packet as a large byte array or a large and matching bits within that array. And all of the forwarding and batching and other behavior that we do really hides the fact that in reality, what this code is ultimately doing is taking some configuration specified in terms of some fairly high level abstraction and processing packets based on what that configuration says. And so configuration, for example, is often specified in terms of things like source and destination addresses in the IP header, or whether the payload is infected for some definition of infected. And this is not extracting this sort of abstract detail from the code is not really simple. But what we want to be able to do is we want to provide a tool to network operators, so we want to really verify invariants that are specified in these terms and not in terms of bit patterns that the packet is seeing. So as an example of this, this is very similar to what I was giving you before, but consider a case where we say, I have this DPI box and I got a set of rules from, I don't know, pick your favorite supplier of DPI rules. And I want to drop all packets that, according to those DPI rules, are going to be marked as being infected. So let's say you wanted to verify this. And of course, you don't have access to the rules at this point, because you just want to verify this for your network. The rules might be changing frequently. How do you define what an infected packet file is in terms of bit patterns? What constitutes a virus has been growing pretty rapidly. And, okay, we're past the point where people use viruses, but still, these attack traffic has been growing pretty rapidly. So, and the other problem with this, which is really one of the reasons to choose this approach, is the code that does this matching is super complicated. It's complex. It's implementing pretty detailed regex matching. How do we use that? So in this work, we sort of take a different approach. So what we see is, if we look at Middleboxes, one can model them as this 4-stage pipeline. They receive and classify some packets. So this determines what sent a packet, whether a packet belongs to a connection that had infected data, et cetera, et cetera. Then based on this, it updates some state that is required for classification. So this could be, if you're an IDS, it could be the TCP reconstruction buffer, where you're reconstructing the payload. Then it updates some state that's used for forwarding. So this is something of the form, did this connection previously send an infected packet? I remember this, and I use this to make my forwarding decision. And finally, you forward or drop packets. And this is always simple, because it looks a lot like all of the match action rules that we've been seeing so far. So in this work, we use oracles, or basically under-specified functions, to model the first bit. And we do a more complete specification of the forwarding model. So more particularly for oracles, the things we record are what are their dependencies, what packets do they need to see to actually take any action, and what is their output. In the SMT terminology, this would be called an uninterpreted function. The forwarding model, as I said, is much more complete. So let me actually show you a real sample model from the paper. So this is the simplest example that was in the paper for a firewall. And the idea is here we drop packets for two reasons, either because the packet is blocked due to an ACL or because at some point a malicious payload was detected. So to mark things as malicious, we have an oracle that decides whether the connection has any malicious traffic sent or whether the packet is malicious. We have a state that says, have you ever marked this connection as being tainted? And then we have a forwarding model that basically tells you what anything should do based on this. And so now for the SMT solver, what it can very simply do is it can look at what are the possible values that the malicious abstract function can return, and it can use this to decide if the classifier worked correctly, would it in fact drop packets that were malicious. So you can in fact verify policies that remember are being, or invariants that remember are being specified in terms of these high-level policies. Now, I won't have time to go into the network forwarding model in detail, but basically we build on the idea of network transfer functions, which is what HSA, Veriflow, and any number of these things have been using. Even Netcat, if you squint at it, basically has this thing inside it. And as I said, we just build on this. The basic idea here is you take all of the switches and routers in the network and you abstract it away into one big switch. So now your network looks like it has one big switch with lots of hosts and lots of middle boxes sticking out of it, and packets flow between these various devices. And details for this are in the paper, so I encourage you to take a look at that. OK, so far I've talked about a mechanism that allows us to abstract away a lot of details. And I've talked about abstracting away both the middle boxes, large parts of the middle box code and large parts of the network. The question, though, is how do we scale verification? And the reason this still continues to be a question is that in reality, networks are huge. So for many of these stateful things, for example, for the cache example that I showed you, you need to consider you might need to consider a large part of the network, or it might not appear obvious how you can consider a smaller part of the network. And in that case, you have to deal with networks where, for example, like Google, you have 900,000 machines connected into one internal network. And even if you're an ISP, maybe you have smaller numbers of machines, but you still have these large installations at your edge. And the thing is, as we've moved to things like NFV, the number of middle boxes here has only increased. So in the case of Google's data center, almost every machine acts as a middle box. If you think back to Daniel's presentation from yesterday, every vSwitch had the NF stack, so this is exactly the same idea. So the question then is, how do we address this scaling? So we've already taken some steps to doing that, which is we use these abstract models for middle boxes, which allow us to not hit things like the undecidability boundary that Leonard was just talking about in the Q&A. We abstracted away the network, which even for work like HSA has been essential to allow it to scale to very large networks. But it turns out this is not enough, because one of the things we showed in a previous paper is that once you add in state, the problem itself is X-space complete. And more practically, what we find is for any reasonably sized network, our SMT solver starts timing out because it sees this huge formula. It cannot actually solve this. Now, this might seem like a problem for us because we chose to use an SMT solver, and we could have been like SymNet and use symbolic execution or something. But really, this isn't a problem exclusive to this. There is no way around this. You have a pretty large state space to explore. Any technique that you use is just a search technique. It is going to have to explore the state space. So basically, the problem is all of the techniques we have so far work well for small instances. How should we expand them to large instances? So in our work, we build on two techniques. We use what we call slicing and symmetry. which I'll talk about briefly. Actually, I'll talk about slicing briefly. Symmetry, I'll just express in the evaluation part. So for slicing, the idea is very simple. You have this large network. Could you find a smaller equivalent of the same network that minimizes the number of devices that you have to consider, but any verification results there still carry over? And the idea behind symmetry is obvious. Networks tend to be very symmetric. Policies tend to be very symmetric. You can leverage this symmetry to just reduce the overall number of invariants that are present in a network. So if you have a bunch of hosts that belong to the same tenant, you don't have to verify rules for each of those hosts. If the hosts share rules, you can just verify for one of them. So this is basically what I've been saying. So slices, as we already said, are subnetworks of the original network. But what we need to establish to make sure that, so remember, the point here is we want to pick a smaller network, and we want to make sure that any verification we do carries over. The way to do one technical way to do this is to establish a bisimulation, where the idea is for any step you take in the big network, you can find an equivalent step in the small network. Now, because you can find these equivalent steps, what the SMT solver is essentially doing is it's searching for a sequence of steps that lead to a bad property happening. So if there is a sequence of steps in the whole network that leads to a bad property, then an equivalent sequence of steps will also exist in the small network, and the SMT solver can find it because hopefully there's a smaller number of steps happening in the small network overall. The unfortunate thing is it's not always possible to find these, but let's start by just giving you an example of what they look like. So here's an example network with lots and lots of Acme characters. And the basic idea here is, suppose you want to verify something about the Roadrunner and the Coyotes server. So obviously, any subnetwork where you want to verify this invariant, just for this invariant to be meaningful, you have to pick the machines that are specified. You need to pick everything that's on path, and maybe this is sufficient as far as you're concerned, because now I can just prove path properties about this. The problem is that the cache throws a wrench in this, so we also need to pick another animal to show what would happen if there was an additional user in the network. And we have proofs in the paper that show that this is sufficient. So once you have all of this in place, you have established a bisimulation, and you can prove invariance in the slice. Now, remember that we had to pick an extra animal. Can we always figure out what is the minimal set of things to pick to form such a bisimulation? As I already mentioned, the answer to this is no. We give a couple of techniques in the paper to find these slices. One of these depends on the fact that many middle boxes have a state that is partitioned by flows. Some of these depend on the fact that many middle boxes don't care where the state is set from. For a cache, I only care where the content is cached. I don't care what the history was leading up to the content being cached. In both these cases, we have a way to find slices, but there's an open question about what are the limitations, what limits do we need to place on NFs to make sure that you can always find slices. So basically, what is a tight bound on when you can find slices? OK, let me quickly show some evaluation. First, we'll consider a data center where we've used a very simple set of policies. We use what are standard AWS policies. We allow each tenant to have some public and private hosts. And we want to verify three things. First, we want to make sure that private hosts for one tenant cannot reach another. We want to verify that public hosts for one tenant cannot reach private hosts belonging to another one. And finally, we want to make sure that public hosts are always reachable by everyone. So public hosts are things like my web server. I want everyone to have access. Private hosts are things like where I put my payroll. I don't want anyone to have access. There might be an interface that allows the web server to display how much money I earned last year or something. So if we use slicing and we use all of our techniques, you can see that we can verify this in about a tenth of a second, and this time is basically independent of the number of hosts that we have to consider and the number of tenants we have to consider. So in this particular setup, every tenant has the same number of hosts, so the number of hosts and the number of tenants is proportional. However, if we didn't use slicing, as you can see, we see a pretty rapid growth in verification time. In fact, this is in log scale, so you can see that we are seeing an exponential growth in the time taken to run this verification, even as we are linearly increasing the number of hosts. So this shows you that slicing is essential to getting some of the performance that we've been seeing. So I briefly mentioned symmetry previously. The basic idea behind symmetry is probably clear, but just to show you how much it matters, we took a paper from IMC 2013 published by Microsoft on some data center bugs they were seeing. And we basically tried to use our tool to check whether we could prevent these bugs. Basically, could we find them ahead of time in buggy configuration? So what we found is that the amount of time it takes grows as a result of the number of symmetric groups that we have. So another way to look at this is, if we had only had 1,000 hosts and we treated them all as asymmetric, it would have taken us about 300 seconds to prove a certain property. But because we considered symmetry, and if it turned out that because of symmetry there were really only 25 different unique symmetric hosts that we had to consider, it would take us less than a second. So symmetry plays a huge role in actually allowing us to scale these techniques. So in conclusion, stateful networks are very important now. We need to start worrying about how to verify them. The primary challenge is scaling to realistic networks, for which we have to abstract. And to do this, we definitely have to abstract some things away. But what we abstract is an important, gives us some flexibility in terms of what we can verify or how we think about these networks. And finally, even after we do abstractions, it's important for us to have a way to do compositional verification to actually scale to realistic network size. Thank you. Hey.
Leonid Ryzhik from Our Research.
Yeah.
So how far is your modeling language from being a programming language? Assuming that this, uninterpreted functions become external functions that can be done in different languages.
That's a great question. So it is quite close to being a programming language. If you look at prior work, for example, if you look at the symbolic execution work, they do have a programming language called Stateful. The problem with network functions in particular is the programs that seem to be easy to model or easy to convert into models that we can feed into Z3, and the programs that seem to perform really well and process 100 million, or okay, no one processes 100 million on a single core, process like 20 million packets on a single core, seem to look very different. So that's the part that I don't know how to reconcile. If we could reduce the number of things that we wanted to do with our NS, or put a boundary on these are some building blocks that we want, what we have is pretty close to a language that allows you to build network functions.
Thank you.
No. Hey, Rodrigo.
Hi. Thanks for the talk.
Yeah.
So I'd like to know if you can provide some intuition on what kinds of middle boxes are easy to abstract away. You had a very simple middle box that had one Boolean. So what is easy, what's hard to express, and how do you know that your model of a middle box is correct?
Great question. So let me start with the first one, and then I'll give you the second one. So for the first one, in reality, so remember, we are just hiding some details. It's easy to hide details for anything. The question is how much those hidden details matter or do not matter to the results you get. So for example, even for an IDS, you can hide away the entire matching thing. We have an example of an IDS in the paper. But you could then say, but if you're the person who writes signatures, that's probably not good for you because you want to know if the signatures are correct. If you're the person who uses signatures that were generated by someone else, then that's fine for you because you trust the signature provider. So I think most things are easy to model. It's just the level of abstraction is for us right now is quite high. To your second question about how do they match, largely it's because we model these middle boxes fairly abstractly. So one way to look at it is there's this RFC that lists out a set of middle boxes, which I'm sure you've seen. I don't remember the number anymore. I'm sorry. But you can take those things and you can produce a model for any one of those things, for any one of those types, or a few models for any one of those types that closely corresponds to what you actually find in terms of what the configuration looks like and everything else. So the main thing then that you need to write is a translator from their configuration language to whatever configuration language your model provides. So in terms of how closely they match, currently the answer is by inspection or by code analysis or by code review you find this, but they are simple enough that it should be easy to do that analysis.
Thank you.
Thanks.
Thank you for your work. I guess it is very interesting given these stateful data planes like P4 are becoming very popular. One quick question.
Sure.
Given we also had the buzz work last year in NSDI,
Yes.
do you have any head-to-head comparison in terms of performance and properties? I'm just curious to know whether your work is more scalable or buzz, or which one is faster. What are the the limitation of it?
That's an excellent question. I have. There's a couple of aspects to that answer. The first is the way Buzz is designed to work, it generates test traffic that you send through a network, and then you analyze to see if your network did something bad in response to that test traffic. So in our case, we are not going through a test network, so everything is happening within your computer in some sense in an SMT solver. There, you're actually sending packets. Which of those is faster sort of depends on how quickly you can generate and analyze the entire traffic on the entire network. That's the first one. The second thing is more generally, Buzz does actually use some versions of models of a middle box. They happen to be written in C++ and look a lot like code, but because of the same thing that I was explaining to Leonard, there are limitations to what they can model or not model. So just in terms of generality, there are many devices that do not fit into the Buzz model, while they do fit into ours. So it's just that's one difference that exists.
So do you also have performance numbers in the paper?
I do not have. So I have performance numbers in the paper for my code.
No, I mean comparison between Buzz and yours.
I don't, because they're fairly different systems, as I said. Like they're doing test packet generation. We're doing this. Means I know most of the Buzz authors quite well. We've discussed the differences many times before. It's a different task. Like one is sort of a more online. I generate something and I wait to see what the network does. So how do I account for the time it takes for me to test what the network does that?
Okay, thank you.
Thanks.
Yes, thank you.